All of this is specification. So we still have no code. Okay, so the code is here. Implementation. The code is the event-based component model. That's what we call it. It's the model used in the book by Luis Rodriguez and Rashid Gharoui. So this is the pseudocode we're going to use in this course for defining our algorithms. This is the best model that I know of, except there's actually some PhD theses which introduce better models. But in general, this is the best model for writing these distributed algorithms, because they can have failures, they can have weird synchrony, so they get kind of subtle. So this is the best model for that. There is no programming language that supports this model. That's weird, huh? People keep using these ancient caveman languages like Java for doing complicated systems when they're completely the wrong model. There's actually one language which is the closest one is Erlang to this. Okay, the closest one, but even so, there are many things in this model that are not in Erlang. So the closest industrial language to this model is Erlang, and that's why we see Erlang in this course. Okay? Okay, so that's what we're going to see today, but first I want to finish last week's course. So last week we introduced causality. So you remember causality when you have events in a distributed system. So I'm going to go over it quickly and just give you the intuition, okay, today, and finish what I could not finish last week. So here you have events, okay? So these the pink circles is a chain of events that are causally connected. Now, you notice that we have 3 different executions here. So an execution is a sequence of configurations with their events in time, huh? So the first one, the second, the third. So it's like a concurrent system, huh? You have these events and you have these transitions, the configurations. Now these 3 executions have the same causal connection between the events. So you can see the pink sequence here is the same, and this yellow one is the same, but the events can be changed, and there's more possibilities, huh? So all of these 3 executions are going to compute the same thing. So we say they're part of the same computation, okay? So as long as you change causality, you're not changing anything, in fact, okay? Okay? So basically, so theoretically, executions are similar if the causality is the same. And that means if you're on a node, you cannot see the difference. Huh? If you can only observe events coming and going, you cannot see the difference between 2 similar executions. So they are equivalent. So the equivalence class is called the computation. Okay? That's one thing. So we actually have a theorem then. So the theorem is basically what I just said. If I take an execution and I move around all of the events here, but I respect causality, that means I will never put an event, if an event is causally before another one, I'll never put it after, okay? I will never make time go backward here. So these F events, they're the same as the E events, but switched around. But if one F event is happening before a J event, I'm sure it's going to be before here, which means in the time, huh? The time is going like this, huh? So I'm never traveling backwards in time. That's logical, huh? So all these executions are going to be similar. So if you move around the causality, nothing's changing, okay? So there's some conclusions you can make. One, it's very interesting. If you take any distributed algorithm in our model, we're talking about our model where we have events, computation and delivery events, there's no algorithm that can observe the sequence. Basically, they can see this picture. There's no algorithm that can print the picture of what it did. I mean, during the execution, you can collect information, and at the end, you print this picture. That's not possible. Or this picture. You cannot distinguish them. The algorithm cannot make the difference. Okay? So that's a conclusion. So basically everything happens in a world where things are the same if they're causally the same. Okay? So that's important intuition. And that's in our model. You can extend the model, which I'll show you in a minute, to break that. But if you do that, you introduce maybe other problems, though. So assume that you can print the diagrams. This is a proof by contradiction. You take two similar executions that preserve causality. The final configurations are exactly the same. If they're the same, they can't print different diagrams, okay? They cannot observe the order, the actual order of events. So an execution cannot tell whether it's here or here or here. When you get to the end, you don't know which is the order. Any order that's respecting causality is possible. Okay? Here's another result. You can extend the model if you want to know. If you want to know the execution order, you have to use a different model. Okay, so this theorem holds in the model we defined last week. Remember I told you when you define a model, it has to be strong enough that you can prove impossibility results. Okay? So in the model we defined, there's no hardware clocks or anything like that. It's just a sequence of events. So that's basically correct. So if you want to see the order of events, you have to add something like a hardware clock. If you add a hardware clock on each node, then you are no longer in the model. Okay? If you have a hardware clock, so each process can read the clock when there's an event, and so the final configuration will have different values for the clocks. So it won't be the same anymore. If you look at this picture here, if each of these processes has a hardware clock, and whenever there's an event, it reads the clock and puts it in a special register somewhere. Of course, this clock here, P1, is going to be different from this clock, so the final configurations will actually be different. So we're not in our model anymore. We're in a different model where we have hardware clock. But a hardware clock is a nasty thing. You don't want to assume right away to have hardware clock, okay? Hardware clock is a nasty thing. So you can do hardware clocks, and these machines do have clocks. But clocks are very hard, actually. First of all, it's very hard to keep them synchronized between different nodes. And so it adds another level of complexity. So we want to avoid the clocks. Okay? So what we know is that causality, everything is causality, okay, in a distributed system. Everything is how the events are related. If you move them around and they keep the same causal order, then nothing changes. Okay? So now, I want to compute causality. So we have defined it theoretically, how the events are happening before the other events, and then there's this transitivity rule that actually makes all of them connected. But that's a God's eye view. That's a view from outside. I want to make now, inside the algorithm, I want to compute this causal order. And that I can do. And that I can do, and there's no contradiction, because all the similar executions will have the same causal order, of course. So the causal order is always going to be the same. Okay? So I can compute it. There's no contradiction. So there's two most important ways to compute it, and it's called the Lamport clock and the vector clock. So these are techniques that you can add to any distributed algorithm. You can piggyback them, okay? So these are called logical clocks. Okay, logical because they're not timed in seconds. They're only ordering the events in order, 1, 2, 3. So they're not actually hardware clocks. Huh? They're not ordering in terms of seconds or hours or minutes. They're just ordering the events numerically, okay, with integers. So they're called logical clocks. So the simplest one is the Lamport clock, invented by the guy who you will find everywhere, who is Leslie Lamport. Long time ago, before you guys were born, he invented this. The guy's very old now. Okay? So it's very easy. Each process has a number, an integer, a counter, an extra variable, which I can call t, and initially it's all 0 on all the processes. And then when the algorithm executes, I'm going to increase the t's. Okay? If I do a count event, I'm just going to increment. T gets t plus 1. Okay, that's easy. But on a delivery event, it's a little bit more subtle. So on each message that I send, I'm going to add some information. I'm going to add the value of the t from the sender, and when it arrives, for example here on a node P, I get a t coming from another process, Q, and this is my local one. I will do the max of those 2 plus 1. So basically, I'm looking at all the events that happen before me, but also before on the other process. So if you make a picture, sort of looks like this, huh? So here we have the processes, P1, P2, P3, so the numbers are 0. So here I have an event, and then it becomes 1. Here I have an event, becomes 1. Another event becomes 2. And now I have an event that puts a message in the outbuf, and a delivery event here. Okay, here it becomes 2. Okay, but here there's a 1 piggyback here. So now I will do the max of these 2 plus 1, which is 3. Okay. But now let's say I have a 1 here. Okay. And now if I do another message here, then this one will become 4. The 3 will go on there. And between 1 and 3, I will do the max plus 1. So it becomes immediately hops to 4. What does that mean? It means if I look at this event, what's the intuition? The intuition is that there are 4 events causally before this one. Okay, here there's only 1, but here there's a chain, okay? There's actually 4 events, 1, 2, 3, 4, that are causally before this one, that I know about. Of course, I don't know everything here, huh? I only know when the process sends me a message. So the Lamport block tells me something about causality. Okay? You see how it's being calculated? So what does it tell me? If the event A happens before B, then the T of A, which is the Lamport clock of A, will be less than B. So if A happens before B, so for example, if A is here and B is here, these 2 events, and we know that A happens before B, then 2 is less than 4. Okay? And we know it's not the case that B happens before A. Okay? So the Lamport clock, if I have 2 events that are causally related, it will tell me which one is earlier. Okay? But that's not telling me everything, of course. Huh? It will not tell me everything about causality. For example, if I have another event here, C, or here, let me do this one, C. C has a Lampert clock of 1, A has a Lampert clock of 2, but C is not before A. You see, so it only works if there's an actual causal connection between the two. And then it tells you the direction. So it's actually, the Lampert clock is only give you half of the information. You see that? It's not telling you everything. It's not telling you between A and C which one is before. Well, these two are concurrent events, A and C. And this C could be here, and this one could be earlier, and that would be fine. So this 1 and this 2 doesn't say anything when you have the events are concurrent. Doesn't tell me anything. It only tells me something if there's already a causal connection. So, for example, if I have this event, D and A, you see that D and A both have the same number, 2. So the Lampert clock is not a unique thing. And there's actually many events that have the same numbers. If I have this one, E and F, E, F, and C all have Lampert clock of 1. So it's not because the clock is the same or different that I'm learning something. So the Lampert clock is the simplest one. It only says one thing. If there is a causal connection, it will tell me the direction. If A and B are causally connected, so A is before or B is before A, then I can compare them. You see that? That's all it's telling me. But we can still do something interesting with the Lampert clock. We can make a nice trick. Okay? Let's say we want to invent a total order of events. We want to invent some order that we can compute that will take all these events, A, B, C, D, E, F, and rank them in a total order, which is the same everywhere. Of course, the Lampert clock is not good enough, because E and F and C have the same number, so they're not ranked. So we want them to be in some order, okay? Maybe like this, I don't know, but some total order. Now, the Lampert clock is not good enough for that, but we can do a trick. We can actually use the Lampert clock and add something to it and get a total order. And what we do is we combine the Lampert clock with the process ID. So the process ID is their number here, 1, 2, 3. Each node has a unique ID. So we have pairs, TPP and TQQ. These pairs, we can define a total order for them. Okay? It's very simple. If the two processes are on the same node, then we just compare the Lampert clocks. So if we have T1, 1, and T2, 1, they're both on P1, so they're both on the same process, and then we just compare them. It's clear that E is before A. Okay? Okay? But if they have the same value, so if we have T1 with some number and T2 with some number, we have both of these are the same. That's possible, That's only possible if P and Q are different. So E and F have the same Lampert clock, but they're on process 1 and 3. So in this case, you compare P and Q, okay, to break the ties. You see that? So either, the idea is if the two Lampert clocks are the same, then you use the process ID to break the tie. Okay? So if I have event 5 and event 7, it'll be less. But if I have two event 4s, they they have to be on different processes, huh? They cannot be on the same, otherwise it's the same event. Then we will assume that 2 is less than 3. P2 is less than P3. So we can use the Lambert clock to build a total order. That's actually interesting to know that. This is actually a practical thing. You see the subtlety? It's a little bit subtle, huh? The Lambert clock is telling us causality, and then we're adding a tiebreaker to give us a total order. So this total order has nothing really to do with causality, yeah? This total order is just a total order. It's not really causality because C and E are concurrent, huh? And in the total order, E will be before C, yeah? Because P1 is before P2. But E and C are concurrent events. So this total order has nothing to do with causality anymore. But it is a total order. That means any node which computes it will come up with the same order. And then you know why that's interesting? Actually, that actually has an application. If I have a distributed database, okay, with 2 replicas. So here's an application for that. So here is a node P1, P2, and I'm sending update events to the database. So the update event will, and it's a bank account. And this one will multiply by 2, adding 2% to the account. 2%. And this one will add 10 euros. Okay, so I have 2 updates for my bank account. And these are 2 copies of a distributed bank account. And you know that the bank has to have copies, huh? Well, if these 2 events arrive in different orders, then the 2 values will be inconsistent. They won't be the same. If I add 10 euros and then I add 2%, it's not the same as adding 2% and then adding 10 euros, huh? Because in this case, on the left, the 10 euros, I will also have 2% on the 10 euros, and here, the other one, I won't. But if we use this total order, if we use the total order that I just defined here, and we have these 2 update events, then we can ensure that they will be done in the same order, okay? So if 2 users do an update event, like let's say C is an update event, E is an update event on different nodes, and then I send that to the database copies, I can put these in the total order, and then I know which one has to be done first. You see? So this is actually a useful technique. So the Lambert clock lets me do a total order. Okay? So here's an example of a calculation. Lambert clock. So I already showed you one. Here's another one. 0, 0, 0. So I do 1. And then it becomes 2. And then it's 3. This one now becomes 1. Okay, that one becomes 4. You see how this one works? This 4 comes from 3, the max of 3 and 0, plus 1. I need to do the max on both of them, huh? So that becomes 4. And then if I keep going, I get also 4 on point P1. And this is a 5. And that's a 6. Okay? So that's the first kind of algorithm we see in this course. It's very simple, right? Okay? And how to use it to make a total order. But the Lambert clock is not really good enough for causality. Because it's not telling us that E and C are concurrent. Both of these are 1. So they're the same. It's not really telling us anything here. Huh? So we need another kind of clock. We need a better clock. So how could we do that? We need a more sophisticated clock to actually tell us when the events are concurrent or not. So the Lambert clock will not do it. Huh? So we need a smarter clock. So unfortunately, Lambert invented the Lambert clock before inventing the smarter one. So his name got attached to the stupider one. And the smarter one is not named after a person. It's named the vector. It's called the vector clock. Actually, it's not that easy to have all the information on causality, you need to keep a lot of information for that. So in fact, each process has to have a vector of size n. So n is the total number of processes. Huh? Each node has to have a vector which gives you a number for all the processes. And then whenever you get a message, you will do the same kind of calculation as Lamport, but in the vector. So again, you will piggyback the vector on every message. You see, it's already more expensive than Lamport. Huh? Lamport, there was only one number you had to piggyback. Here you have to piggyback n numbers on every message. And if you have 100 nodes in your system, 100 extra numbers for every message is kind of expensive. So this clock is more expensive. And the way you update it, it's very similar. Okay? So you increment locally P. P is where you are. Okay? Whenever you do a transition, you have a local event happening. It's either deliver or comp. You're always having a local event. Huh? But then, if it's a message coming, you also look at the vector and you do pairwise maximum. So you actually do the maximum of the two vectors, pairwise, okay? So you basically are keeping track of the vectors instead of just numbers. And now you're good for causality, yeah? With the vector clock, you know everything basically, yeah? On causalities. So you can compare. So these are vector clocks. So these are the vectors of n, huh? So Vp is less than or equal to Vq if it's less than or equal for all elements. And it's strictly less than if it's less than or equal, and at least one element it's strictly less than. Okay? So you can actually compare the two vectors, okay? But sometimes you cannot actually order them. You can actually say if Vp and Vq are concurrent, if it's not the case that Vp is less than Vq, and it's not the case that Vq is less than Vp. So it's not always the case that vectors are comparable. Huh? I mean, you can see simply how that can work. Huh? I can have 1, 0 as one vector, and 0, 1 as another vector. This could be Vp, this could be Vq. These two cannot be compared. Huh? It's not the case that one is less than the other. These are concurrent. And this corresponds to a case where I have one event here. So this is P1 and P2. So I have one event here. So here I get 1, 0. And here I have another event. Here I get 0, 1. So these are two concurrent events. And the two vectors are not comparable. Okay? So the vector clock gives you all the information. Okay? The vector clock gives you, in addition to Lamport, so Lamport does the second one. Huh? If A happens before B, then the clock is less than for A. But Lamport does not give you the first one. So you can actually say when the events are causally connected. If VA is less than VB, then A happens before B. Okay? So VA is the vector clock. Huh? So the vector clock, it's an if and only if. It's directly giving you all the information on causality. And it's not that hard. I mean, you need to piggyback these vectors, and you need n vectors, n numbers per node. So it's a little bit more expensive. So here's an example. I have 0, 0, 0 on all three, first of all. And now I'm going to calculate the vectors. Huh? So this one becomes 1, 0, 0. Then it's 2, 0, 0. Okay, for the second one. If I do another one now it's going to be 3, 0, 0, because that's an event. Huh? The send, which means I put something in the outbuff, that's an event. So I have to increment also when I send. Huh? So here now I have, this one becomes 0, 0, 1. Notice what happens here. I increment this one first, 0, 1, 0. So that's this event. Huh? And then I take the max, element-wise. So the thing becomes 310. Huh? So this 310 is actually telling you a lot. It's telling you that this event, there are 3 events on P1 that are causally before it. There is 1 event on P2 that is causally before it. And there are 0 events on P3 that are causally before it. Okay? This is telling you, summarizing this event with respect to all of the previous events. You see the intuition, what it's telling you? So the 3 is how many events are before it on P1. The 1 is how many events are before it on P2, which is basically the receive here. Huh? And the 0, we have nothing yet received from here. There are no events on P3 that are known to be before this one. Yes?
Would it not be good to put an extra number to count the number of processes we met? Because if we went on P1, P2, and P3, we have the real value.
Sorry, I don't understand. Say again. Maybe take off your mask for a minute, just as...
If we go only on P1 and then on P2, the value, the third number, 0, is not true.
This one?
No, the next.
Which one? This one?
Yes, 0 is not true.
Yes, it is true, because this one, this is all the events on P3 that we know are less than this. This event is actually concurrent with this one, eh?
Okay.
You see? There's actually 0 events on P3 that we know have to be before this one, because we didn't receive any messages yet. See how it works? So this 0 is correct, huh? And there's this event, there's 1 event, there's 3 events on P1 that we know. If we had more events here, for example, here, they would not be in the 3, because they are actually concurrent. It only becomes causally connected if there's a message. If there's no message, there's no causal connection, you see? So since there's no message from P3, in fact, this event is not causally connected, you see? I mean, it's a good question, huh? Because this event, the 001 event, is not before this 310, huh? It's not before. In fact, these are concurrent, and if you put this one later, it doesn't change anything. And the reason is, it only connects if there's a message going between. You see that? It's for everybody, yeah? You see that? There has to be a message. Otherwise, they're not causally connected. So the vector clock keeps track of all the ones, all the messages in all the processes that are causally before me. So this event has 3 events on P1 that are before me, 1 event on P2, which is this one, and 0 on P3 that are before me. Okay? It summarizes the number of events on all the processes that are before me. That's what it tells you. Okay? Intuition. You have to have the intuition of what it's telling you, these numbers, huh? I mean, yeah, you calculate the numbers, but you have to understand what it means, huh? So I go on. So this is 400. This one will be 320. And what's this one going to be now? You tell me. What's this one going to be?
322.
322. So I'm going to increment this one, and then I do the max. Huh? Okay, because I have to count the delivery event too. Huh? So it's going to be 322. Huh? You see that? So the intuition is this event here. There are 3 events on P1 that are causally before me, 2 events on P2 that are causally before me, and 2 events on P3 that are causally before me. We assume that this event, that I'm just after it. There are 2 events that are before me on P3. So this is summarizing the knowledge of the causality of all the nodes with respect to me. Okay? That's the intuition for the vector clock. Yeah? This is a nice clock, but finishing a vector clock actually is kind of nasty, because there's no way to compress it. I mean, many clever researchers have tried to keep track of causality with smaller things than n size vectors. Doesn't work. If you want to keep track of causality, you need vectors of size n. So if you have 100 nodes, you need 100 length vectors. Okay? And then you can do, sometimes you can do tricks like build your system in hierarchy, but at the end of the day, the vectors, you have to keep track of them. Yeah?
Can the vector clocks be used to handle distributed systems in which we don't know the number of nodes?
Ah, no, that's the problem. See, if a new node comes into the system, you have to update everybody's vector clock, a new extra element. So the vector clock is designed for a system where you know the number of nodes. Of course, you can do more complicated things. You can actually, if you have systems where you add nodes dynamically, then usually you will not use vector clocks. They're too complicated. You will only use it on systems with small number of nodes that are fixed, like distributed database is typical. Usually in distributed database, you have replicas, maybe 3 replicas or 5 replicas. So you have a small number of replicas, and that number is like fixed, unless a replica fails or something, but most of the time it's the same. So the vector clocks are used on these smaller kinds of systems. But typically servers, when you have a number of replicas. Cloud systems usually have these groups of replicas that are used to maintain consistency, and usually that's a small number and it's kind of fixed. But this does not work like with millions of Facebook users. No way. No way that every Facebook user is going to have an element in million element vector. No. And it's true that Facebook does not guarantee causality. It tries. But sometimes there's a mistake. But usually you don't really notice because you're not really intensely looking at every single thing on Facebook. But if you have a busy system on Facebook with many people interacting, Facebook can make causality mistakes. So usually you don't notice because there's not that many. But it's not practical for them to use this vector technique. Okay? So this is typically used on smaller systems. Okay? So now I'm going to make a small little quiz just for you, just to make sure to see whether you have precise thinking in your heads. Okay? So you know what a partial order is, and you know what a total order is, right? If I have a number of events or things, partial order means that some of the events are ordered, but some are not. And total order means that they're all in a linear order. Okay, they're all sequenced. So here's 3 relations that we've seen. And you're going to tell me what they are. So happens before relation, causality. Is this partial or total? It happens before relation. The one we've been talking about for the last couple of hours. Is it partial or total?
Partial.
So it's partial, huh? Yes, of course it's partial because you can have concurrence events. What about the less than relation on Lamport logical clocks? Notice this is a relation between integers, huh? It's just comparing 2 integers. So is this partial or total? Trick question. I'm telling you it's a trick question. You have to think a little bit. Is it partial or total order, this less than relation on Lamport clocks? If you strictly think in mathematical sense, is it partial or total?
Total.
Total, huh? Yes, it is total. Because you're comparing 2 integers, or 2 natural numbers. And all natural numbers are in a total order. So it doesn't mean at all that you're ordering the causality. It's just the order between the values of the clocks. Huh? So what about the less than relation of vector timestamps? So these vectors timestamps are not integers, huh? They're vectors of natural numbers, huh? So this comparison of the vector timestamp, partial or total?
Partial.
Partial, yes, because it's exactly reflecting causality. So the two vectors could be incomparable. Whereas for integers, you can always order the integers or the natural numbers. Huh? Okay? Okay. So this is the summary of the two. So Lamport says, if you know the causality, if you know there is causality, it tells you the order. The vector tells you both directions. So you can actually, it'll tell you if there is causality or not, which the Lamport will not. So which one do you think is more useful, in fact? What do you think? If you now practically want to use it, if you want to do causality. The vector clock is actually more useful, because it actually tells you if there is a causal connection or not. That's usually the thing you want to know. Huh? If I have two messages coming in on a chat, two messages coming in, I want to know which order they should be displayed. Well, in order to do that, I need to know the causal connection between these two messages. Are they coming from different conversations, or they are inside one conversation? I need to know the causality, if I want to do a chat correctly. So usually, within a chat, Facebook or Reddit or whatever, they usually do a little bit of effort to try to keep track of causality. Because for conversation in a chat, it's very weird if you get the answer to a question before the question. So if somebody asks a question on one node, the message goes to another node. That person answers the question, and you are on a third node, and you receive these two. These two events are causally connected. The question is before the answer. But you are receiving them on a third node. So you have to see them in their causal order if you want to have a reasonable conversation. So for a conversation, this vector thing is important. So usually for smaller things, usually there's not a million people in a conversation, so you can actually keep track of causality. Okay, so I'm not going to go over this. So this is the summary of the causal stuff. I want to say a little bit about complexity. So now I want to show you something about timing. Okay, so we know causality now. We know how things are executing. And so I want to show you something about time, how long something takes, but in the model. So the model does not have hardware clocks, but that's not so important, the missing hardware clocks. Really more important is how many messages, okay? And how many comp events, okay? So when an algorithm, all of the states are terminated, and there's no more messages. So that's the termination, So the algorithm is done when all the nodes are done, and there's no more messages hanging around in the network, in the in or the out buffs. So the network is empty, So that's termination. So how do we compute the time for this? So there's actually different ways. Okay? So one of the complexities is how many messages. If I have n nodes, they can send lots of messages between each other. They're loading the network. So this is called message complexity. So the maximum number of messages for all admissible executions. So this is a worst case. It's like complexity of algorithms. The O, big O notation. So the big O gives you an upper bound. Remember big O. So this is also an upper bound, worst case. So all admissible executions. So admissible means fairness. That means all of the nodes are working, all the messages are arriving, and you do all the executions. So the causality can be different for these messages. And the causality is different, so maybe okay? We'll see what effect that has, okay? That can actually have an effect on the complexity, on the maximum number of messages. So how many messages until termination? This is the message complexity, okay? It's kind of like what's the load on the network. But it's not the same as how much time it takes, huh? Because you can have n time steps, but many more messages going around, okay? Because each process can be sending messages on every step, okay? So the time complexity is a different thing. The time complexity is how much units of time, okay? So basically, we're going to look at the comp events, okay? So a comp event, okay, is a computation, but actually we're going to assume the comp events are 0 time, okay? Because in a real network, computation is usually very fast compared to the network. So the real time comes from the messages. So this is kind of a funny definition, huh? But it's realistic, okay? Because usually the comp events are negligible compared to the messages. So we're assuming the message delay is at most 1 time unit. So sometimes messages will be slow, but we're assuming we're actually counting the message delays, huh? So we're saying a message can be like 1 unit, even if the message is very slow, okay? And the computation events are 0. But the message are at most 1 time unit. So a message could be 0 or 1, okay? So then we can look at how long the whole thing takes, okay? Each comp event has a number. It's the same, kind of the same as a Lampert plot, but this is a time number, huh? So the first event happens at time 0. The time will not decrease. It can only increase. So the maximum time between a comp sending and the consuming, so the message sent and the receive is 1 unit, which we said here. So the time complexity again is a worst case. Maximum for all admissible time execution. Okay? So this is a kind of a funny way of measuring time. But it's essentially tracking the message, the longest sequence of messages. Huh? Okay, so I'm going to show you an example of this. This is actually a little bit paradoxical. You might think this is a very weird definition. Why are the message delay at most? Why isn't it just 1? Here I'm saying message delay is 0 or 1. And I'm doing the worst case. So I'm going to give you an example here, an algorithm. So we're going to compare 2 ways of doing it. We have each message takes exactly 1, or each message takes at most 1. Now, intuitively, it's not really clear which one is the best, huh? Maybe the exactly 1, intuition might tell you it's better approach. But in fact, the exactly 1 is actually a bad definition. And I'll show you why. If I assume every message takes exactly 1 time unit, then this definition is not going to give me realistic results. Okay? If I assume that every message is 0 or 1, it will be realistic. Okay, and I will show you an example. So again, this is, I take a step back now. Again, this idea of message complexity is defined in the model. And again, we are using the model to deduce things about reality. Okay? So the first question is the definition the right one? Okay? So we have now 2 ways of defining message complexity. One where the messages are always taking 1 unit, and the other one where the messages take 0 or 1. And in both cases we do a worst case. Okay? Now, it turns out, let's compare intuitively the two here. So we have two models of doing message complexity. And maybe I should make a picture here to give some intuition of what's going on here. Because there's kind of a paradox here. So here I have a set of executions. So these are all executions, okay? And each one of these has a message complexity. So here, this is the set of executions where the messages take 0 or 1 unit. So all of these executions are executions where the messages take 0 or 1. And now I have another set where they take exactly 1. Where do I put that other set compared to this one? Here I'm assuming messages are taking 0 or 1, but if I assume the messages are always taking exactly 1, then any execution where the messages take exactly 1 is going to be inside this, right? Yes, because 0 or 1 is also 0 or 1. Huh? So the messages take exactly 1 is actually a subset. Is actually a subset of this set of executions. Huh? In this set, these are all executions where the messages are taking 1 time unit, and I'm taking the max over this. Huh? Worst case. This is all the admissible executions. And then I assume the messages can also take 0, so that means I'm putting in executions where some of the messages are 0 here. Huh? And so these are executions which are not in this set, but they're in this bigger set. And then I also take the max. Huh? Okay, so how can we compare these two? So when there's there's actually more executions here in this one. You see that? And all the executions in this smaller subset are in the bigger one. What does that mean? It means that the max in this bigger set is always going to be greater than or equal to the max in the smaller set, right? Right, huh? Because it's a superset. What does that mean intuitively? It means that if you allow the message to take 0 time, that the message complexity can actually increase. That means if you allow the messages to go faster, the algorithm gets slower. You see that? That's kind of a it's kind of called the paradox of message complexity. That seems very weird, no? It's actually true, huh? So here is the execution, so small repeat, and then I'll go and explain, I'll show you an algorithm. And you see the intuition. You'll understand why it's like that. So if I let some of the messages go faster, arbitrarily, I'm doing worst case, huh? I can pick freely whichever message goes fast. And I do worst case, and some of the messages in these outside ones, X's, are faster than all the messages in the inner one are always going exactly 1. And because this is a superset, the time complexity of the maximum can only increase. Okay? So how do they compare? So the time complexity for at most can increase. Is that a real thing? Can that really happen? Yes, it can really happen. And here's an algorithm where it happens. Okay? So now let me show you this algorithm. It's actually a fairly straightforward distributed algorithm. So this is a simple broadcast algorithm. So this is one of the first algorithms we're going to see. So this is not completely the same as, it's a little bit simplified compared to our model, just to show you the algorithm, but it's very intuitive, okay? So I have n nodes. One of the nodes is a source, and all the other ones are like destinations. And I want to do broadcast. So how does it work? So I broadcast. So each of the nodes has some neighbors. for example, like this. So let's say this is the source node, and it has neighbors, okay? Maybe it's like this, but it could be more. So how does it work? I send A, this is the message I want to broadcast, to all the neighbors. And then I wait, because I want to know when the algorithm is finished, when everyone has received it. So how does it work? So it sends A to all the neighbors, okay, like that. And the other nodes all execute this code. Okay, the source sends this code, but all the others send this code. So there's two possibilities. Either it receives A or it receives B. So it starts by receiving A. If it receives A from a node P, then it actually has a local variable called parent, where it sets it to P. So the first A that arrives is the parent node. Okay, so here the parent node will be S. Let me number these. 1, 2, 3, 4, 5, 6, 7. So here the parent node will be assigned to S. Okay? And then I forward A to all neighbors except for parent, and I send B to the parent. So I'm going to send A to downwards, and I send B back up. So the B is actually telling the source that I got the A, okay? So all the B's are basically going to go back up to the source. So when the source receives n minus 1 B's, it knows that the whole algorithm is finished, right? Because there's n nodes in all. So then the source can say everybody received the messages. Now we're assuming no failures here. So when I receive an A, I forward to all neighbors except the parent, and I send B back up. And when I receive B, I just forward it back up. So basically, I'm building a tree, okay? So the first node, the first one where I get the A is kind of the parent. And this one, the parent is going to be 1. Here, the A is going to come down, the parent is going to be 2. And here, 7 is interesting because there's 2 A's coming down. And it depends on which one arrives first. So which one is fastest, So assuming that the one from the left comes first, then the parent is going to be 3 and not 4. Okay? So if I receive A from a node and the parent is different from null, then the A is dropped. I do nothing. There's no else case here. So it's only the first A that does something. So this is an algorithm, and you see how it works, first of all. You see how it's working? Basically, you start from the source, the A's go down, and each node will receive A's, and the first A determines the parent. Okay? And then there will be B's coming back up, and they will flow up along the parent connections. You see how it works? You're clear on how it works? Yes?
But then the structure has to be a tree.
It builds a tree. The actual graph does not have to be a tree, but the parent nodes, the parent links actually form a tree, yeah. But for example here, this graph is not a tree, yeah? But there's only one of these that's going to be the parent. So it's kind of building, in the local variables, it's kind of building a tree. But the actual network doesn't have to be a tree, yeah? It can have loops and sharing and whatever, it doesn't matter. But the algorithm will build a tree according to which A's arrive first. Yeah, so there is a tree built internally. It's kind of what's called a spanning tree, yeah? But the network does not have to be a tree. It can be arbitrary network, okay? Now, the question is, what is the time complexity of this? If every message takes at most 1, so I'm talking about the A and the B, yeah? Or if every message takes exactly 1. So my question now for you is, show me a network. So it depends on the network, yeah? Show me some network where the at most time complexity is strictly greater than the exactly. It's funny, huh? You can actually build a network where the at most time complexity will be strictly greater than the exactly time complexity. So that's an exercise for you. So these two complexities, for the at most one, you are free to choose whatever time you want for every message, 0 or 1. You basically have to take the maximum over all choices, huh? Where the exactly one, they will all take exactly 1. So at the at most one, each of these A and B messages will be 0 or 1, and you are free to choose whichever one time you want, huh? Okay? See that? And so my question for you is, find me a network, doesn't have to be a very complicated one, an actual network where this at most one complexity is strictly greater than that, so that the algorithm actually slows down if you allow messages to go faster. It's funny, huh? It's a paradox. It slows down because you're allowing messages to go faster. It's amazing, isn't it? Okay. Okay, so that's an exercise for you. Okay, so this is actually like an exercise that I want you to think about. And I will give you the answer next week, and you can discuss, but try to find the answer by yourself. Because if you do that, the more effort you do, the better effect will have on your brain, okay? So the answer is not important. The important is, well it is, but the more important is the effort you try to find the answer. So let me give you a hint for this. Okay, so let's tell you. So at most can only raise the complexity, okay? Every execution with exactly 1 unit is also possible in the at most model. But the at most model adds more executions, ones where you have some zeros. So the problem is, the issue is the time complexity, it's not the time of 1 execution. It's the worst case over a whole set. So all you have to do is find 1 very bad execution. Of course, there's going to be many of them that will be better in the 0-1 case, huh? But maybe some will be worse. You only have to find 1 very bad one, and then the complexity goes up, huh? It's the worst case. So here's an intuition for you. In the R example, broadcast. The A takes 0 or 1 time unit, the B takes 1. Okay, let's do like that. Now here's an idea. You put the network. So here I'm giving you a big hint. Long A paths could be very fast, okay? But the B paths will be very slow, okay? That's all. Think about it, okay? It's in the slides, it's in the Moodle too, huh? I'm not going to say more because I want you to think about it. Okay? Okay, now let me go. Let me start a little bit. Now we're going to start, if this thing will work. Yes. So that's an exercise, huh? And the exercise is on the slide and it's on the Moodle. So there's no lab session, but I encourage you to take some time and to try to find the answers. To understand why this paradox of message complexity. Why is it like that? And when you understand it, you will have gained something. You will get something. You will understand something new. You will have a deeper understanding. Okay? When you understand that. So do a little bit of effort. Just a recommendation. Okay. Now I want to talk about, now we're going to start coding. I gave you general knowledge about causality, about complexity. Okay, fine, that's that concept. But now we want to actually write code. Okay? So we're going to write code. And we're going to specify the code because we want to know exactly what we're writing. Okay? So that's what I want to talk a little bit about in the time that's left today. So we're going to write very sophisticated distributed systems in this course. Okay? And this is, typically it looks like this. A distributed system in a real system will look sort of like this. So here you have the nodes, a node, a node. The node is connected through what I call a channel, which is the network. This could be TCP/IP or whatever. You have some application here running. Could be a browser, whatever. And then you have some algorithms, some distributed algorithms that are in between the application and the channel. So this is kind of what we're concentrating on here. Huh? So this is usually called middleware or whatever. So we're going to be doing lots of distributed algorithms in this middle layer. Okay? And so why do you need a middle layer here? Well, because TCP is not strong enough. TCP will only do point-to-point reliable streams. That's fine, but it's not enough for applications. Okay, we need more than that. Okay? The network protocols, it's a good start. And so the work, we need them. Absolutely, we need them. So I will not fire my colleague Olivier. I will keep him in the department. Okay? But it's not enough. We need more. We need more, and so I will hire me to do more. Okay? So we need more. So TCP only does one-to-one. One node to one node. But very often you need more than one. You need group. You have a group of people discussing, for example. Or you have a group of nodes implementing a distributed database. Or you have some kind of an algorithm where you have lots of nodes coordinating things. It can even be like in a house. You have Internet of Things, where you have your house, lots of little computers connected, and they're looking inside of a room with sensors. And so they're all working together on figuring out what's happening in that room. So that's a topic I know about. That's called sensor fusion. So they're actually working as a group. So you need group operations. So here's some group operations. Broadcast. So I showed you simple algorithm before the break, but that algorithm does not handle failure. That's a way too naive one, okay? In the real world, the broadcast has to work, even if there's failure. And of course, it's concurrent. So we're going to see those algorithms. So the first one we're going to see is reliable broadcast, which even works when there's failure. And then there's other ones, causal broadcast, which you need like for chat, respecting causality. Total order broadcast, which I mentioned already in the first lecture. And then funny ones like terminating reliable broadcast, which I will explain later. So this thing you need, but you need other things too. Shared memory. If I have a distributed database with transactions on many nodes, so conceptually, each node is a replica of the memory. I'm doing a transaction on all of those, which is a complicated operation. I'm doing many transactions concurrently, and this is a shared memory. So all this is shared. So all these nodes are talking together, and they have to be doing the shared memory in a nice way and not getting everything messed up. Or you have consensus, where the nodes have to agree. For transactions, you need that. Atomic commit is a form of consensus. Also, group membership. Maybe you have a group where you know who's in the group and you know who's not. So they have members, and the members are allowed to do something. Maybe those are the ones discussing. So you have groups, you maintain the group. So you need all this kind of stuff, extra. And that's only a subset. There's many more. You need many, many things. Okay? In addition to TCP. So I call these services, high-level services, in middleware. And they have to be reliable. Reliable high-level services. You need all that stuff. And they have to work on real internet. So in the worst case, they have to work when failures happen, and when it's concurrent, and when the system is partially synchronous. So that's not so simple, okay? So one example is reliable broadcast. So reliable means that it works even when there's failures. It has to be reliable. And what does it mean? In our case, we will say, when I do a broadcast, either everybody gets it or nobody gets it. All or none. Nothing else is possible. So that's reasonable, huh? Because if there's really a lot of failures, then maybe the message just disappears. It's possible for there to be too many failures, and if the nodes that know the message fail, then nobody gets it. But in the other case, it should not be that only some of the nodes get it. They should either be all or none. So we're going to see this algorithm, okay, in 1 or 2 weeks. We're going to see it, or you're going to see the code for it. And it will work correctly, and it's completely concurrent, so anyone can do broadcast anytime, and failures can happen at any time, to any node, and it's correct. That's complicated, huh? So we're going to use our model for that. And you'll see it's actually not so complicated if you understand the model. So the second example is atomic commit. So the nodes have to reach the same decision. So here it's whether to commit or abort a transaction. So you know transaction has to be coherent. So if many nodes do the same transaction, either they all do it or nobody does it. So they have to agree, all of them commit or all of them abort. Okay? So that's a consensus problem. And also nodes can fail anytime. And there can be many concurrent transactions happening. And the whole thing has to work. So it's concurrent and partial failure. Okay? And the system is partially synchronous, so we don't even know how long the messages take. So that's kind of nasty, isn't it, to write these algorithms? If I ask you to invent this kind of algorithm, not so simple, the code for that, huh? Okay? So that's what we're going to see also in this course. We're going to see those code. We're going to see the code. Now, the thing is, the way you write the code, the language or the paradigm is very important. If you do it in the wrong paradigm, it gets really complicated. But if you do it in the right paradigm, it's actually not that complicated. Okay? Okay, so I'm going to define a pseudocode, which doesn't have a really nice name. It's called the event-based component model. Okay, but it's like a programming paradigm, and it lets you write things, but it's a pseudocode, so it's not. There's no real system that does this. But the closest real system to this is Erlang, but even this it's different still. Okay, so how are we going to do it? So each node, so let me see, I'm not sure this is the best explanation. Okay, so remember the model that we had. Each node was sequential. Each node does either a computation when it does a step, or it delivers a message. And then there was different messages. In our model, okay, we have receive K messages in the in buffs, send one message to each neighbor in the out buffs. So this is the model we saw. There's other models where you receive one and send one, where you at most receive one, send at most one. So these are all different models. But this is all kind of the same. That's not very important. Okay? We're going to abstract away from this and make kind of a simple model. So the nodes will be executing programs. So I'm going to make some pictures also. So I want to give you the intuition of this. So each node is going to execute a set of modules. So the nodes are going to be kind of like this. This is a node, this is another node, and there's layer. So there's going to be a layer, layers of this. Okay? On each node, kind of like a stack. And if I have a yellow, then I can make it look like that. So this corresponds to the yellow. Each of these are yellow boxes. So this yellow box is important. This yellow box is like a concurrent thing. Okay? It's like a concurrent agent. It receives messages and sends messages. Okay? So the notation I'm going to use is kind of weird. Upon event is basically receive, and trigger is a send. But why did I pick those weird names? It's not my fault. It's the fault of these guys. So if you don't like it, send a hate mail to Rashid Gary and Luis Rodriguez. I actually know both of those guys. They're very nice, but maybe they're not the best in picking nice names. I don't know. So upon event means I wait for a message to come, and I can receive a message. And that's this receive event thing with argument. So that's a message. And then I do some local computation. So this is sequential. I'm just executing stuff here, and I can send messages too. So the send is called trigger. That's very weird, but it's a send. It's just a send, okay? So upon event is the receive, and there's like a pattern. So it waits for a certain kind of message, and when the message arrives, then I can execute this, and this is like a single-threaded thing, okay? So that's the basic building block of it. So we're going to see lots of examples of this. Huh? So the messages are called events. Why are they called events? Because it's most of the time they're regular messages, but they can also be timer results. There can also be Boolean conditions. So the upon event thing, the upon event, it's usually going to be messages, but there might be like a Boolean condition there, or it might be timer thing. So it's not just messages. So that's why they're called events, okay? But you can consider them to be like kind of messages arriving, okay? And these nodes will be sending messages to each other then. So let me make, these are all the yellow boxes. Each of these yellow boxes is like a single threaded thing. So this is node 1. This is node 2. There's some network connection. The network is between the lowest layer. Then you have upper layer, and the top layer is basically the application, okay? Application layer, whatever. And then there's more layers. There could be many layers in between. So there's messages. Some of the messages go down, and some of the messages go upward. So, for example, this guy could be a broadcast component, and this node on the application wants to do a broadcast. So it sends a message saying, I want to broadcast, okay? And then this lower one could be the link, the communication link. So maybe when I invoke the broadcast will start sending messages down, messages will come here, go back, and eventually there's going to be some result coming back up. So you see, messages go down and up, and there can be messages going across from the lowest layer, uniquely from the lowest, okay? So I have here a send, and I have here a receive. The send will be called it's called trigger, and the receive is called upon event. Strange names, but why not? Okay? Then at least you don't have the bad intuition if there's already used. So when I request something from a layer, I'm sending a message down. So this is always layered, huh? So these messages are called requests. The messages that go down are called requests. The messages that flow up are called indications. Okay? Again, thank you, Luis and Rashid, for these wonderful names. So when I send a message down, it's a request. When I get an answer, it's called an indication. It's just a response from the message going down. So both of these are messages, huh? The only difference between request and indication is that request goes down and indication goes up. Okay? And then there's confirmation, which is just a special kind of indication. It's just an acknowledgement, okay? If I do a request, I might have a confirmation, which is confirming a particular request. But it's just a message going out also. But it could be just like acknowledgement or something, yeah? So the two main things are request and indication. So the system kind of looks like this on one node. So here's my application. So each yellow box is like a single thread. Huh? Each yellow box is running separately as a single thread. So here's my application. Maybe it's doing like database. Here I have a commit component, which decides whether I do commit. Here I have a reliable broadcast component. Here I have consensus component. Here I have perfect link. So this one is doing the message between the channels. So the network communication is always the bottom. Okay? So I want to do database operation. I send a request down to this guy. And the code starts running internally. Da, 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 da. Maybe it sends other messages down. Indications come up. It can send requests down. Indications come up. So messages are flowing up and down. Okay? But from the viewpoint of the database, I only see this thing. Huh? All these guys are underneath the commit. Huh? So all our programs are going to look like this. So we're going to show you the code for what's inside those yellow boxes. Okay? That's the kind of code we show you. And just to remind you, the send is called the trigger. The send can be either request or indication. The request is a send that goes down. Indication is a send that goes up. So a trigger can either go down or up. Huh? It's a send. And receive is called upon event. So it basically waits for a certain event, to certain message to come. So it depends. Huh? So if I have two boxes, I can have like this. Trigger and upon event like this. So this is a send. This is a receive, and this thing is a request, okay? But if I have the message going up, if I have the trigger here, and upon event here, then this will be an indication, okay? So send, receive, request go down, indication goes up. So this is the notation, the words we're going to use. So it's important because we're going to use them through the whole course. Okay, so it's always going to be the same words. And you'll see with this model the code will be fairly simple. Okay, so here is an actual application, sort of abstractly. So here I have three nodes, P1, P2, P3. Each node has this stack. Okay, of these yellow boxes. The bottom one is the channel, so these are the network communications. And all the ones here are doing whatever the code is doing. So for example, this is a broadcast. I say I want to do a broadcast of M. This one will send M to P2, M to P3. This one will deliver. So the deliver will be what happens when the message arrives, deliver when this one arrives, so the channel will do a deliver, and then when this arrives, this one will actually send the delivery of the broadcast itself back up to the application. So you see messages are trickling downwards, and then they're trickling back upwards on all the other nodes. Sometimes they can go up and down several times. So you see how it kind of works, this thing? Okay? Let me just say a little bit about how the whole specification looks like. Okay? You have here the requests, the responses. Okay? That's the messages going down, coming back up. You have the properties, you have the model, and then you have the implementation. So let me just say something here. So this is how we specify algorithms. So really important is safety and liveness. And also important is the model. So this is something, when you did algorithms in previous courses, you already see this correctness properties. Huh? So this, you know this, huh? You should know this. That the algorithm is making progress, and that it's doing really good things, no bad things. So you know this, but we're going to go over this again. But this model is a new thing. Model is new because there's many different kinds of distributed systems, and sometimes the algorithm depends on the model. So, failure assumption. Can the nodes fail? How can they fail? Is it Byzantine? Is it just crashes? What kind of failure? And it depends. The algorithm might be really complicated if you have to do failure. Huh? And then synchrony. Ooh, is it asynchronous or synchronous? Very often it will be partially synchronous, because that's the internet case. But this is really important, because if you choose the wrong one, then maybe your algorithm is impossible. So a small change in the model can change a lot the code, okay? And all of this is going to be written using our beautiful event-based component model. Okay? So what should I, let me see. Let me just give him a simple example. And we'll show some very simple things now. Just simple to end simple. So here's a very simple module called print, and it has two events. Request going in, which is print request with data. So this is kind of like a record. Huh? So print request is like the type, and these are two arguments, request ID and a string. So this is a pseudocode. So we're going to kind of assume that all the data types we need exist and that they're nice, okay? And then when you do a confirmation, print confirm, this goes back up, and it tells you this print job, RQID, has been done, okay? And here's the code. Our first piece of code, this is completely trivial. So you have only one little box. Upon event print request, I'm assuming that there's an actual function called print here, huh? Okay? Print string, and then I trigger print confirm. That's it. So here I receive print request, I send print confirm. This is really simple, but you see the idea. But let me at least show you one or two slightly more complicated ones, because everything else is going to be more complicated later on. So here's bounded print. So bounded print, you only can do a certain number of prints, and if you overdo too many, it doesn't work anymore. So you do bounded print, same as before, ID string, and then you get a print status, okay or not okay. So did the print work, or maybe it didn't work? And print alarm means that the number of print requests, there's a threshold, there's a maximum, and you get it back when you reach the threshold. Okay, that's kind of a very weird printer, but it's a nice piece of code. So we have a local variable. So we have three little upon events now in here. And each one of these executes when the event arrives. So when you start up, you automatically have an init event. Okay? And bound is a local variable, which is set to some number, which is the predefined threshold, 1,000 print requests. And then when you get a bound print request, if the bound greater than 0, then decrement the bound, trigger print request. If the bound is 0, then trigger print alarm. So it tells you there's an alarm. Otherwise, here print status not okay if the bound is 0. And if you get print confirm, then you do print status okay. So you see, this thing is already a system with two layers. You see that? Bounded print is implemented on top of print. Huh? So it looks like this. This is one of the most simple examples of two-layer system. I have print. I have bounded print. Okay, so this is my system. So here I do a request here, and then bounded print will use print. Huh? So bounded print will use print So bounded print will actually do a print request going down here. Print request. And actually the print confirm comes up here. Print confirm. So you see that? So this is already a simple example of two-layer system. So bounded print is built on top of prints. So this is really simple, huh? So this printer is really kind of a bogus printer, huh? It's not really doing anything interesting, huh? So the only reason I show you this is because that's how we're going to build our distributed algorithms, like layers. Question?
So bound is part of the variable bound, is part of the internal state of...
Yes. So this bound is a common variable among these three. So technically, these three upon events are executing together in one thread. So when one of them is executing, then the others will not execute. There is one thread actually shared between these three. Since this is one layer, in fact, it corresponds to one layer here. Huh? So if you look at it like this, it's kind of like this. Huh? You can have multiple upons inside. Inside of this thing, you have one thread. This print also is one thread. So there's one thread. These pieces of code will execute sequentially. And there's only one of them going to execute at a time. So they will be. So if multiple messages arrive, you will be executing one of these and then another one. And there's a scheduler here. So if the bounded print request arrives, you can actually do concurrent printing in this model. You can have two bounded print requests arriving before the print confirm arrives. So if you have multiple messages arriving, like a bounded print request and a confirm, then the scheduler will choose one of them non-deterministically. So a message, when it arrives, it might not be executed immediately, but it will eventually be executed. So when the messages arrive, they can be executed in any order. But these three upon events are sharing one thread, okay? So that gives you the whole explanation. So if I have a confirm here and a bounded print request, two messages arriving, then what's going to happen is the scheduler will pick one of them, any one, it's non-deterministic, will execute that one, and then we'll pick the other one, okay? So there's no guarantee of which messages. It's non-deterministic, so it's really a concurrent system. Huh? So that should make the semantics clear, right? Is it clear? So we're going to see lots of code using this approach, huh? And layers, huh? We're going to be building our systems in layers, and we'll be building things that in 20 years ago were considered top-of-the-line research, okay? Were considered incredibly complicated, but I will show you the code in just a few lines. So in 20 years, people figured out how to show these complicated algorithms in a simple way. So this layered approach, you see, really helps to understand. So I still haven't shown it to you, but you will see in the next. So in the next lecture, we're going to start writing code, and then we'll be writing more and more code. So let me finish here. We're done. Okay.